All right, good morning, everybody. Let's continue our lecture with the topics of work and energy. Now, in our previous lecture, we have already discussed about work done. Okay, work done is a transfer of energy by the application of a force, and we also have calculated several cases of work done in different systems. For example, we have calculated work done. Let me go back to the. We have calculated work done, for example, by stretching a spring. Okay, and the spring obey Hooke's law, so that the force is given by F equal to minus kx, where k is the force constant and x is the extension of the spring. And when the spring is stretched by the external force does work, and this input some energy into the system. So the spring will increase in potential energy. The stretched springs store some energy as the potential energy, and that's called the elastic potential energy. And that is why we calculate the work done by the external force. The external force is just balancing the force of the spring. So when we calculate this external force, the work done by the external force, we find that when the spring is stretched by an extension x, the work done by the external force is half kx squared. And we also have studied another cases of a body placed at a certain distance from the Earth. Suppose we have an apple, and we place an apple at a certain distance from the center of the Earth. We call this distance r. And we apply an external force, just balancing the gravitational force of the Earth. And we apply the external force to move this body from infinity to its present position. And the work done by the external force is given by this integral, and that integral gives me minus gmm over r. Okay, so that is the work done by an external agent. For example, a Superman. He moved the ball, he moved the object from infinity to the present position. So again, we calculate the external agent, the work done by the external agent against the gravity force. Now we after calculating the work done in several specific situations, we have to pose a question. We move the object from one position to another position, right? When we calculate the work done. But an important question is that whether this work done is dependent on how we move the object. Okay, if we move it from here to here, then is the work done fixed? Or if we move it from here to here through another path, then we get a different work done. That is an interesting question. So we are going to address this question. Now let's begin with a simple example of raising a ball against the Earth gravity. So we have a ball originally at a certain level, at a certain heights. Okay, so we raise the ball by a vertical distance of x. So we have to apply an external force to balance the gravity. The gravity force is downwards, so we apply an external force to balance the gravity and we raise the ball by a distance x. And so the work done is straightforward. The work done is just the external force. The external force is mg, but in the upward direction, right? Because it's balanced gravity. So I integrated the external force against the displacement x, and of course I get mgx. Now this is in fact the potential energy you get in you learn in high school, right? Mgh is the potential energy when we raise the object by height of h. Okay. Now, but we consider another way to move the object, to move the ball from its initial position to the final position. The final level is here. Okay, the final level is here. But we now, instead of moving it directly to the final position, we first move the ball to a height x plus y. We overshoot the final position by additional heights of y. We go to that level, that high level, and then we move back to its final destination. So what will then be the work done through this path? Well, we have to divide the integration into two paths. The first path is from the initial position to the maximum height. The maximum height is as a height x plus y above the original position. So we integrate the force, external force, from 0 to x plus y, which is the highest position, right? And then plus, we then integrate from the highest position, which is x plus y, to the final position, which is x. So, and the other integral consists of is the work done of this path from x plus y to x. Now, of course, after you vary the integral, you can see the x plus y is actually one is appear in one integral, it appears on the upper limit, and the lower limit, and the other integral, it appears on the lower limit. So when you vary the integral, the upper limit will contribute a plus term, and the lower limit here will contribute a minus term. And so these two terms will cancel each other. And eventually you only got mgx, just like what we got before, right? So it doesn't matter whether you move it directly to the final destination or you first overshoot the final destination and move it back. They just produce the same work done. WA is equal to WB. And if you can extend it further, you extend the argument further. Even if you move it up and down, move the ball up and down for many times, as long as your final destination is this level, is the same level, you always get the work done to be mgx. And that is independent on how you move the ball in the intermediate step. You may be moving the ball around a lot in the intermediate step, but as long as you have the final destination of the ball as level x, you always get the same work done mgx. So we say that the work done is path independent. It is independent of how you move it in the intermediate step. As long as the final destination is given, is fixed, you always get the same work done. Okay. Now, but that is not true for another force. That is true for gravitational force, but that's not true for frictional force, for example. Frictional force always opposes motion, right? As it opposes relative sliding motion between the two surfaces. So if you move this block from this position to its final position, which is at a distance x from its initial position, then the work done by the frictional force will be Fx. Okay, now this is actually the work done against the frictional force. Okay, because when you move the block in this direction, you have to apply an external force in the direction of motion, and that force has to be just balancing the frictional force, right? So you move it slowly and with a constant velocity to the right. And so the work done will be F. Now the small f is actually has a magnitude of the friction, but it is actually your external force because you are now pushing the object forward, right? So you have small f multiplied by x. And if that is a kinetic friction, you can rewrite the small f as mu k mg, the coefficient of friction multiplied by the weight of the object, which is the normal reaction, pressing the two surfaces together, right? So you have the work done from here to here as mu k mgx. But how about if I overshoot the final destination? If I first move the object to a maximum distance of x plus y from my starting position, and then I move back to the final position. So what would then be the work done? What would then be the total work done? Now I would say the total work done would be the sum of these two terms. When I first move the object to its maximum displacement, the frictional force has to be multiplied by the displacement, which is x plus y. But when I move it back, you should note that the frictional force is always in opposite direction to the applied force, right? So if I move the block back, my applied force will be in a backward direction. It's still in the direction of my motion. And so my work done will always be positive. The work done by my external force in pushing the block forward will always be positive. Okay, so that means the other term along this path will also contribute a positive work done by my external force. And so the two terms added together will give mu km gx plus 2y. But of course, this is different from the first case. For the first case, I move it directly to this position, and I got only mu km gx. But now when I move it to the final destination and move back, I get mu mgx plus 2y. So the two work done are different. And that means if you are concerning about friction, such kind of dissipative force, the work done by the external force in going against friction is path dependent. It depends on how you move it. When you move it around a lot of time, you dissipate a lot of energy, right? So your external force has to be input a lot of work, and so the work done will be much larger. Okay, so that depends on how you move it in the intermediate step. It does not only depends on the initial and final position, but also depends on in the intermediate step how you move it. Okay. Now, so a little bit of a warning about notes about the friction. Now, friction and viscous force and the drag force, all these kinds of resistance, they are always opposite to the velocity. Okay, when the object moved in this way, in this direction, the frictional force, the viscous force, always is in opposite direction to the velocity. So when the external force is in the direction of the velocity, the external force does positive work because the external force and the displacement are in the same direction, right? So the external force does positive work. But the frictional force does negative work because the frictional force is in opposite direction to the velocity. So the frictional force does the negative work, okay? And we can say the external force does work against friction, okay? That is what we thought. So in terms of energy, we can think of like this. The external force is providing energy to the system, but that energy is eventually dissipated by friction as heat. Okay, so the energy has eventually gone to heat. Okay, and that is so frictional force is a kind of dissipative force. It converts the work into other forms of energy, and that is heat or internal energy. Okay. So we are now ready to define the conservative force. Its force is said to be conservative if the work done by the force, okay, or the external force, or work done by the external force just overcoming the force. Now, this is the original force. It may be gravity, it may be electromagnetic force. It is said to be conservative if it doesn't work, or the external force just balancing it doesn't work, and that work is independent of path. If that is the case, the force is said to be conservative. Okay, and in our case, we see that gravitational force, at least for where we saw that for the object close to the surface of the Earth, gravitational force is conservative, right? Electrostatic force is also conservative. Okay, but the dissipative force, like frictional force, viscous force, they are not conservative. Okay, the work done is path dependent, right? Now, we only discussed one-dimensional cases, but in fact, you can generalize our discussion to three-dimension. But the three-dimensional cases require the use of some advanced mathematics like line integral. So we skipped it in this course. And if you generalize it to the three-dimension, then if you start from a point P to a point Q, you will start from a point P and move the object to a point Q, then the force is said to be conservative if the work done by the external force just overcoming it is produce a work done that is path independent. So if you go from P to Q along path A, you get the work done WA, and you go along another path, you got WB, and WA is equal to WB if the force is conservative. Okay, A, B are arbitrary paths. That means any two paths joining the point PQ, they produce the same work done. Okay. Now, so having defined the conservative force, we are now ready to define potential energy. So in order to define the potential energy, you first have to have a conservative force. Potential energy can only be defined for a conservative force. Okay, if the force is not conservative, then you cannot define potential energy. And so again, we just apply the external force, just balancing the conservative force. Okay, so we are now applying external force to the system. And the potential energy is defined by what? It's defined by the work done by the external force in moving the object from a reference position O to its final position X. So the function U is the potential energy function. U is a function of X, and X is the final position of that object. And the potential energy is calculated by the work done by the external force in moving that object from the reference and certain reference position we call O to the final position X. So the upper limit in this integral is in fact the final position at which the potential energy of the object is measured. Okay, so it's given by this integral. And if you like, you can express it in terms of the original conservative force, because external force and the conservative force just differ by minus sign. So you get a minus sign here if you express the integral in terms of the conservative force. Okay, so remember that if you are working on the conservative force itself, you have a minus sign here. Okay, and by definition, if my location, if the location of interest is exactly at the reference point, then I put X equal to O, right? If I put X equal to O, then the potential energy at O must be equal to 0. And that means the reference position O is the position we choose, such that the position at that position, the potential energy is defined as 0. Okay. Now, if we change the reference position, then we just add a constant to the integral. It doesn't affect the physics. It will just affect how we define the absolute value of the potential energy. Now, for the example, it's like this. Now, if you have a spring stretched by external force, okay, we apply external force to stretch the spring. The external force doesn't work, and eventually the potential energy store the energy input by the external force, and that becomes the potential energy of the stretched spring. Okay, so the energy has been transferred by the external force to the system. If we have two different positions, P and Q, then the potential energy difference between these 2 points, UP minus UQ, will then be the difference between these two integrals, right? We integrate for UP, we integrate from O to P, right? And for UQ, we integrate from O to Q. And UP minus UQ is just the difference between these two integrals. Now, but if I extract the minus sign O, and in this case, I got an additional minus sign, so that I can invert the upper and lower limit. So when this become a plus sign, I integrate from Q to O, right? So eventually, I got integrating the F from Q to O plus integrating the force F from O to P. So eventually, I get rid of the O, right? And I eventually get an integration from Q to P, right? Now, I write out clearly for you to understand better. Now here, I can write this integral as plus Q over O. I just invert this minus sign to plus sign. And so I invert the upper and lower limit. So it becomes integration of f from q to o. Now the guy in the bracket will be integrating from o to p plus integrating from q to o, right? So the area just add up, right? So that is equivalent to what? That is equivalent to integrating from q to p, which is this integral. Okay. So that is how we calculate the potential energy difference between 2 points P and Q. Now you can see the potential difference does not depend on the reference position. It depends only on the initial and the final position, but not the difference between the two positions, but not depending on the reference position O. Okay, you can see you do not see O appearing in the limit of integration. Okay. So the value of the potential energy, the absolute value, depends on the choice of the reference position O. But the difference in potential energy between any 2 points is independent on the reference position O. Okay. Now, how do I understand this? Now, that language is rather technical, right? So we would like to simplify it so that you can understand it based on the high school physics you learn in secondary school. Now, for example, if I have a table and if I place an object on a table, and if I define this position to have 0 potential energy, this position is Q, then UQ is equal to 0, right? Because I define this position to have a 0 potential energy. So what would be then the potential energy as a height h above the table? If I raise the object up by vertical height of h, what would then be the potential energy at the higher level? At this position we call P. Then of course you know the position at this position the potential energy is mgh, right? That is what you learn in high school. Now, so the value depends on how you choose the reference. If you choose the reference to be the surface of the table, you got 0 potential energy at the table, and at the height h above the table, you get mgh. But how about if I choose the reference position to be the ground? The table itself has a height of vertical capital H. Now, if that is the case, then the surface of the table will have on the surface of the table, the object will have a potential energy of mg capital H, right? Because this is at the vertical height capital H above the ground. Okay, and the potential energy at height h above the table will have a potential energy of mg small h plus big H. Okay, because we are now measuring the potential energy reference to the ground. Can you see that? So the value are different if you of the potential energy are different if you define the reference position to be different. Okay, but the difference in the two potential energy between these 2 points, UP minus UQ, is always mgh. When you minus this from this, the absolute H always gone, and you always get mgh. That is the energy difference between the 2 positions. Okay, and that is independent on how you define the reference position. Now, just there's a joke here. For example, you consider electric potential instead of gravitational potential energy. Now, everybody knows the main supply in Hong Kong has an electric potential of 220 volts, right? If you put your finger to the socket, then you will get an electric shock. Because your potential, your body will have a potential essentially 0 potential, and the main surprise will have a potential of 220 volts. So the difference in the potential between the main supply and your body will drive the current. Will have produce an electric field. The electric field will drive the current to your body, so your body gets hurt, and you get an electric shock, right? Now, but how about that? But what is the absolute magnitude of the voltage is not important. Suppose now we call our body to have a potential of 20,000 volts. That is the arbitrary defined. Okay, we define the potential of our body to be 20,000 volts. But in that case, the potential of the main supply will be 20,220 volts. Okay, we change only the reference position, but the potential difference between the body and the main supply is still 220, which is independent of your choice of the origin. Okay, and that is the that potential difference. It is that potential difference that produces the observable electric field that drives the current into your bodies, and that matters. Okay, and that is a physical origin for you to get hurt. So the physics is not dependent on the choice of your reference position. Okay. Now let's go back to the spring mass system. I stretch the spring by the external force, and I does a work, and the work is given by kx, because of the spring, the force of the spring is kx in the opposite direction. So my external force does a positive work of integrating kx from 0 to x. Okay, and that is become the potential energy. And of course, the potential energy is half k squared. If I plot the potential energy against x, I get a quadratic curve. Okay, so the energy does not increase linearly with x, but it increases quadratically with x squared. Okay, so it curves upward like this. And of course, the reference position here is taken as unstretched position of the spring. When x is 0, which means that the spring is unstretched, the potential energy is 0. Okay. And how about raising the ball? If I raise the ball by a vertical height of x, I integrate the external force mg over the displacement, which is x. I get mgx, and that is the potential energy you learned in high school. And in this case, the potential energy against the heights is a straight line. Okay, it's just linear depending on the heights. Okay. Now remember, in here we have plus mgx because we are considering the work done by the external force. Plus mg is in fact the external force. If you want to go back to the conservative force, which is gravity in this case, you have to add a minus sign before the conservative force. Okay, so the conservative force in our case is the downward gravity of mg. Okay, which is minus mg. And if you express the potential energy in terms of that conservative force, you have to put additional minus sign here. But of course, the two minus sign here will cancel, and so that gives you just the mg, the plus mg. Okay. How about the object that is placed very far away from the Earth? When we calculate the potential energy, we calculate the work done by the external force in moving the object from infinity to the present position. So that means the reference position in this case is chosen at infinity. So that means when the apple and the Earth are separated by a large distance, we define the potential energy of the apple to be 0. That is what we mean by defining the reference position. Because we integrate from infinity to r, right? In our previous example, we integrate, you may wonder why we do that. We integrate from infinity. Now we have the answer, is that we want to calculate the potential energy using the infinity as the reference position. So we calculate the work done by the external force from infinity by moving the object from infinity to the final position, r. Okay. So in that case, we have the plus gmm over r squared, the integral from infinity to r, and eventually we get minus gm over r. That is the potential energy at this position. Now the potential energy due to the gravity of the Earth is negative. Why? Because the potential energy at infinity is taken as 0. So the potential energy closer to the Earth will have a minus sign because it has a lower energy than infinity. Okay. So that is the potential energy curve. If you plot U against R, you will get a negative value. And because of one of R dependence, it goes to infinity. It goes to negative infinity when R tends to 0. Okay. Now we can also derive the force from the potential. Now in our previous discussion, we define the potential energy by using an integral of the conservative force, right? We have integrate the external force from reference position to X, right? We got the potential energy. But we can now go back, okay? If you are given the potential energy, you can find the external force or the conservative force by using a differentiation. Okay, how do we do it? The answer is easy. We just apply the fundamental theorem of calculus. The differentiation is the inverse operation of integration. So how to get rid of this integral? We differentiate it. We differentiate both sides of this equation. So the left-hand side becomes du dx. And the right-hand side will be differentiating the integral of f dx. Do not forget the minus sign because we now are talking about the conservative force itself. Okay. Now the differentiation actually acts on the upper limit. It does not act on the dummy variable inside the integral, but it acts on the upper limit. Okay. So differentiation cancel the integration, and the f is evaluated at this upper limit of x. So we got minus fx. And that is a fundamental theorem of calculus. Now, so we have find f from the potential. If you are given the potential energy u, you simply differentiate it with respect to x and add a minus sign, you get the conservative force. That is a rule, okay? When you go from the force, the conservative force to the potential energy, you add a minus sign to f, you integrate from O to x, you get the potential energy. When you go back, you start with u, then you differentiate x with respect to x, add a minus sign, you get f. Okay, so the f and u, they are just connected by the fundamental theorem of calculus. You integrate f, you get u, but you differentiate the u, you get f. Okay, and do not forget, there's always a minus sign here. Okay. Now, an interesting features about this relation is that the conservative force is always pointing, is always in the direction of decreasing u. Now, for example, if u is increasing with x, then du dx is positive, right? When u is increasing, du dx is positive because u is increasing. But with a minus sign, that means the force is now in the direction, or in the opposite direction, is in the direction of decreasing u. Okay, and on the contrary, if u is decreasing, then du dx is negative. If I add an additional minus sign, that means the conservative force is in the positive x direction. It is in the direction of decreasing u. So the interesting thing is that the conservative force always points in the direction of decreasing potential energy. Okay, now this is when I say like this, it's a rather abstract. So let's look at the cases that we have studied. Okay, now for example, for a stretched spring, we have the potential energy as half kx squared. Is that right? So the u increase with x, like a quadratic curve, increase with x curved upwards, because u is proportional to x squared, right? When I differentiate this, du dx, I get plus kx, right? Because now you see the slope is positive. When you differentiate it, you are finding the slope of the curve u. And for this case, you find that the slope is positive. So you have plus kx. But do not forget the minus sign. The conservative force is minus du dx. So when you add the minus sign, the conservative force is pointing to the negative x direction. And that means the conservative force is what? Is pointing in the direction of decreasing u. Okay. How about this case? This case is raising an object near the surface of the Earth. Okay. The potential energy is mgx, right? So du dx is just mg. And when you add the minus sign, to du dx to get f, you get minus mg. And that is, again, pointing in the negative x direction. The slope is of the curve is positive. So u is increasing. But the f is pointing to the direction of decreasing u. So you goes down the slope, right? Again, this you go down the slope. And how about the object that is placed very far away from the Earth? The potential energy goes like this, minus gmm over r, right? When you differentiate with respect to r, you get plus gmm over r squared. Because differentiating 1 over r, you get additional minus sign, right? So the minus sign cancels with this minus sign, and you get plus 1 over r squared. But do not forget the minus sign before du dr to get f. And so the gravitational force will then be minus gmm of r squared. So again, you can see the slope to the tangent is in a positive direction. But eventually, you add a minus sign to get the conservative force is points in the negative r direction. So again, it's in the direction of decreasing potential energy. So you always remember this. The force is in the direction of decreasing PE. Okay? So you just imagine, for example, this is a hill. If you place a ball here on a hill, in the middle of the hill, and it roll down, then the ball, of course, will roll down along the slope, right? It will roll down to the position of lower potential energy, right? So it roll down like this. And that is the direction of the conservative force. The conservative force always tends to make the object to have a lower potential energy. It always makes the object to have a lower rolls down the potential energy curve. Okay. Now then we discuss the equilibrium position. What is an equilibrium? If a body is acted by an external force, like a conservative force, for example, we are talking about conservative force, then the point at which the conservative force vanishes when the conservative force is 0, that is called an equilibrium position. Okay. Now, but we have defined that the conservative force is given by minus du dx, where u is a potential energy. Is that right? So if I have a conservative force being equal to 0, that means du dx is equal to 0. And that means by elementary calculus, u may be a maximum position or minimum position. If I plot u against x and find the point at which du dx is 0, that means the slope of the curve is 0, that corresponds to either a minimum position of the potential energy or a maximum position in the potential energy. Now, we study these two cases. First, we look at the cases for minimum in the potential energy. So the curve is like this. It is a minimum position here. And at this position, the slope of the curve is 0. So the force is 0. So the object has no force acting on it at this position. But how about if I slightly displace the object to the left or to the right? If I displace the object to the right, okay, the idea of conservative force tells me that the conservative force always points in a direction of decreasing u. So if I move the object to the right, its potential energy is raised, and the conservative force will direct me back to the equilibrium position because it's always pointing in the direction of decreasing u. So it goes back. It makes my object to roll back to this position, right? If I move my object to the left, again, the conservative force points in the direction of decreasing U. So it makes my object to roll back again to the equilibrium position. So what does that mean? That means this position is stable. If I slightly displace the object to either to the right or to the left, the conservative force always tends to move my object back to the equilibrium position. And that's from a stable equilibrium. So a stable equilibrium means that if I have a small disturbance about that equilibrium, the equilibrium will be restored. Okay. Now, how about if the potential energy curve has a maximum here? So this is a maximum in the potential energy curve. At this point, F is 0, no force acting object. But when I slightly displace the object, you can see the slope is now negative when I displace to the right. And so the force, the conservative force will be positive, meaning that the object will be further displaced from the equilibrium position. It will roll down the slope of the curve, right? So it goes away from the equilibrium position. Again, if I displace the object slightly to the right, to the left, the object will roll down the potential energy curve. It will move away from the potential energy maximum. So that means it is unstable equilibrium. Okay. Now the easy way to understand it is to use a bowl. 一個碗啊. If you use a bowl and if you use the bowl upright and you place a small marble in the middle, that is a stable equilibrium position. When you slightly displace the marble, it rolls back, right? So that is a stable equilibrium position. So the marble rolls back and forth above that equilibrium. But if you invert the bowl, make it at the top, if you place a marble here, it will roll down, right? It will not be stable here. It will roll down, and that corresponds to unstable position, unstable equilibrium position. Okay. Now, having defined the potential energy, we are now ready for the conservation of mechanical energy. That is a central part of this chapter. How do we define the conservation of mechanical energy? Now, I think you have already seen this result in your high school physics. But in high school physics, you restrict yourself to uniform acceleration, right? You restrict yourself to a constant acceleration. But we now extend our discussion to a variable force with a variable acceleration. So again, we start from F equal to ma. I write F equal to m dv dt in differential form. And starting from Newton's second law in this form, I'm going to show you that the work done by this force on the object, when the object moves from here to here, from x1 to x2, its velocity change from v1 to v2, I will be able to show you that the work done by this force is exactly equal to its change in kinetic energy from here to there. Okay. Now, so we start with Newton's second law, acting on force acting on this object. And we multiply both sides by the velocity of the object. So the left-hand side become mv dv dt, and the right-hand side become fv. Is that right? Now we move the differential dt to the right-hand side. So mv dv is equal to fv dt. But what is v dt? I claim that v dt is just dx, because I know that v is equal to dx dt. So by moving the differential to the v side, I got dx equal to v dt. What is the meaning of this equation? It means that in a very small time interval dt, the velocity at that time, at that instant, is v. And if you have a small time interval dt, then the displacement in that small time interval is just equal to the velocity multiplied by the time. So dx is just v dt. That is what the equation means.
So instead of writing v dt, now I write the x, the distance, the small distance moved by the object in that small time interval. Okay. Now we can integrate both sides, right? I can integrate both sides. So on this side, I got integrating f from the initial position x1 to the final position x2. Okay. And the corresponding change in the velocity is from v1 to v2. So on the left-hand side, I only has a function. The function is solely expressed in terms of v. Okay. So I can integrate v against dv from the initial velocity v1 to v2, because the right-hand side is solely a function of v and independent of other things out. So I can integrate it. And of course, integrating v against dv, I get half v squared. And when you vary at the upper and lower limit, I get half mv2 squared minus half mv1 squared. Now look at this equation. What does that mean? Integrating the f equal to half mv2 squared minus half mv1 squared. This is exactly the work energy theorem you learned in high school. In high school, you define the kinetic energy as half mv squared, right? So half mv2 squared is a final kinetic energy, and half mv1 squared is the initial kinetic energy. So the final minus the initial is a change in kinetic energy. I call the change in kinetic energy delta K. And what is on the left-hand side? The left-hand side, as I defined it at the beginning of this chapter, the left-hand side is the integration of f over dx, which is the work done by the force. So that means the work done by the force is equal to the change in kinetic energy. So that is the special case for the work energy theorem. Because the work done input or taken out some energy from the system. So that will change, in this case, that will change the kinetic energy of the object. Okay. Now I assume that apart from the force F, there's no other force acting on the object. So the force F does some work, and it will change the kinetic energy of the object. It will either increase or decrease its kinetic energy, depending on the work whether work is negative or positive. Okay. So that is a special case for the work energy theorem. Okay. Now, I prefer here to have a break here.